All right, so let's look at the first question. It asks us to provide the appropriate reagents to achieve the following synthesis. Now you can disregard the second part here because obviously that doesn't matter. I didn't write the question the same way I ended up putting it on the paper. So the first thing you should look at is the starting compound and what kind of product you get after the reaction has taken place. Compare the functional groups and then compare whether you've added or subtracted carbons in any way. So here we have an aldehyde and we're converting it over to a hydroxyl group, but keep in mind that you've got a hydrogen here and in the end you've added a CH3 group. So this is obviously a reaction that involves addition of carbons, and so far we only know of two. We know of terminal alkylation, which involves a terminal alkyne, which then gets deprotonated and acts as a nucleophile to attack an alkyl halide. And then you have a Grignard reaction, where you have this an aldehyde or ketone, which is attacked by a Grignard reagent and then becomes a hydroxyl group, but you've added a carbon. So it's likely we're going to use the second in this case because we already have an aldehyde or ketone. We don't need to convert it. So what am I going to add? I'm going to add a CH3 group, so I want that to be a part of my Grignard reaction. So the first thing I'm going to do is add my Grignard reagent, CH3 MgBr. I'm going to follow that with a water step, H2O, to protonate my alkoxide anion that's produced from the reaction. So I've accomplished the first step. Now I got to think about the second step. I'm taking my alcohol, which is a secondary alcohol, and then converting it over to a ketone. Now this is an oxidation reaction, and obviously there are a group of reagents you can use, but remember that certain things are stronger reagents, and they're more useful in this case. So because we're going from an alcohol to a ketone, we want to oxidize it, and we would use PCC in CH2Cl2, or we can use chromic acid, which is a stronger oxidizing agent, Na2Cr2O7, followed by H2SO4 and H2O. And in this case, you can use either of these reagents because this is a secondary alcohol. If it was a primary alcohol, you wouldn't want to use chromic acid because you'd get a carboxylic acid out of the reaction. And here we want a ketone, so it's safe to say we can use both of them. In this case, there isn't any selectivity. Now, this reaction from the ketone to this alcohol can seem sort of tricky, but ask yourself again, what am I changing? I'm converting our ketone to an alcohol, first of all. That's important to know. There are only a subset of reactions that can do that, but remember you're adding a phenyl group to it. And that means you're adding carbons. And we already did that at the start. So what we need to do in essence is repeat that. But instead of having a CH3, we use whatever this group is over here, and it's phenyl. So we have in our first step, phenyl MgBr, phenyl magnesium bromide. And then in the second step, we have a protonation step. So we use H2O. So that was relatively easy. Now we just need to use, for the next step at least, methods from Organic 1 that'll help us out. So here we're converting a hydroxyl group into, or the functional change is from a hydroxyl to an alkene. And this is an elimination reaction. So you need to think of stereospecificity, regiospecificity. You need to think about whether OH is a good leaving group. And if it isn't, is there a way I can convert it? Now you can do that in multiple ways, but for this case, we're going to use in our first step something to make OH a better leaving group. So TSCl in pyridine would be a nice one that tosylates the hydroxyl group, and then we're going to eliminate it. So you can use any base. In this case, it doesn't matter because there's only one beta position, or rather here, there's only one beta position to deprotonate from. So we would use sodium methoxide, NaOMe, to accomplish this reaction. Well, now how do we get from here, our alkene, to our bromine? Obviously, this is going to be an addition reaction, but we need to consider the types of reagents because obviously there's a disparity between the substitution across the double bond. We're adding the bromine to the least substituted carbon across the double bond, so this is an anti-Markovnikov addition. And we would use HBr, because that's what we would normally use, but because we wanted to add anti-Markovnikov, we would use a peroxide too, so ROOR. And finally, in the reaction here, we want to convert our compound to magnesium bromide from Br, and the easiest way to accomplish this is to treat our compound with metallic magnesium in some sort of ether. In this case, it would be diethyl ether. So we add Mg, usually a comma over there, and diethyl ether. So 2 ethyl groups projecting from our ether compound. All right, now we're proceeding pretty close to the end. We've converted successfully our Br into a magnesium bromide group, which makes it a Grignard reagent, so don't forget that. It's a Grignard right now. And we want to convert our Grignard reagent to an aldehyde. Now, a lot of students get confused with this particular reaction, and I understand why. Normally, the Grignard reagent is put above the arrow, and the aldehyde is put, or the aldehyde or the ketone is put as the reactant. In this case, we're doing something else. A Grignard reagent can only be used to attack a carbonyl group, which becomes an alcohol after the reaction. Then that's the only thing you can do. But this requires more than one step, because this isn't an alcohol as a byproduct, or it's the end product. It's an aldehyde, so we'd probably need a step that involves oxidation. So how many carbons are we adding on? We had 1 carbon over here, and that's carbon 1 over there, but we need to add an extra carbon to this. So how would I proceed with this reaction? Well, in the first step, I have my Grignard, but now I need something that the Grignard will attack. I need a carbon group that resembles our compound over here, so formaldehyde is a good compound. It contains 2 H's and essentially 1 carbon with a carbonyl group on it. It gets attacked by the MgBr, kicks off its electrons, and then gets protonated in this step to form our hydroxyl. But we don't want a hydroxyl from the end of the reaction. We actually want our aldehyde back out of it. So how would I accomplish that? Well, I'd oxidize it again. And this time, I need to make sure that I use PCC in CH2Cl2, because if I use chromic acid in this reaction, I'd actually get a carboxylic acid and not the aldehyde product that we want. So I stick to using PCC in CH2Cl2. And finally, I want to get back all the way to the very end, because I like to make you guys work for it. Essentially, going back a step, if you think about it. I want to reduce our aldehyde to a primary alcohol. And I would do that. You can use one of 3 methods, but the easiest would be to use lithium aluminum hydride, LaH, and followed by water, H2O. So, a pretty long question, really complicated, but it involves things that you've seen before in class, and it was a little bit difficult right over here, but I think that should be okay. You guys will probably do well if you attempt several problems like this, and if you're able to synthesize compounds with ease, then I think you're pretty set for your upcoming exam.